Hi, this is Noson Yanofsky. We're doing analysis of algorithms. We're going to do the introduction and chapters 1 and 2. Okay, so a few quick things. Here is the syllabus. Basically, the course is called CISC 3220. We meet wherever we're supposed to meet, whatever day. Office hours, I'm always available after class, before class, and here I send me an email. Okay, the most important thing is this book. This is a text-based book, and we're going to talk a lot about this book in a second. You have to buy the book. You have to own the book. You're going to not like the book in the beginning, but you got to read it. It's very, very, very important. I'll talk about the book a lot in a second. Okay, the class consists of 4 quizzes. You have to do homework. At the end of every section, I'm going to say, okay, we're now finished. I'm sorry, at the end of every chapter, I'm going to say, now we're finished. Okay, and you have to do the homework problems. The homework problems are from the book. I gave it to you already. It's in the back of the syllabus. It says schedule and homework. We follow this schedule and we do the homework. It says section 1.1, you do problem 2, 3, 4, 5. Section 1.2, you do 2, 3. Etc., etc. You'll be able to read it. And this gives you exactly the schedule of what we're doing in this class. Okay? The other thing I want to say is if we're going to have 4 quizzes in a 14-week course, that pretty much means every 2 to 3 weeks we're going to have another quiz. Quizzes are going to be 4 questions each, and you're going to have to write pseudocode, etc., and things like that. Okay, let's talk a little bit about the course. Okay, first thing first. Okay, the course discusses how to write programs or how to look at algorithms and find efficient algorithms. We want to know what's done efficiently, what can be done efficiently, how to make programs more efficient, better, quicker, etc., etc. You don't want your computer games to be slow. You want them to be quicker, and that's what we're all going to do. But it's not only quickness we're looking for. We're going to look for speed. We're going to look for clarity of writing and stuff like that. So we're going to do a lot of that, and that's what the course is going to be about. Okay, let me just give you a broad overview of what the course. The course is not hard for the following reason. The first 3 or 4 chapters, we basically do an introduction, tell you what it's about, etc., etc. Chapter 3 has a little of the math and the notation we use. Chapter 4 talks about recursion, which is something we're going to use over and over. Okay? And then for the rest of the semester, we do this topic, that topic, this topic. They're not connected. So if you're lost in chapter 7, don't worry. You'll catch up in chapter 8. So in that sense, it builds a little in the beginning, and then every single week, pretty much, we're going to do a different topic. And so you won't, even if you're lost, you won't get lost. Also, you won't get lost because you can watch these videos over and over, again and again. Okay. First, let me tell you why it's fundamentally important to take this class and to do well in this class. Because this is a senior class. This is what's called a capstone class. You do this when you finish all your other classes. Now, when you go for a interview for a job, if you want to be a developer, not every computer scientist wants to be a developer, but if you want to be a developer, they will ask you questions from this class. They're not going to ask you questions from introductory programming class. They're not going to ask you questions from data structures class. They're going to ask you questions from this class because this is the highest class. And every single computer department has an algorithms class. Data structures and algorithms, sometimes algorithms. So everyone knows it. Okay? And so they're going to ask you questions from this class, not everything else. So if you want to get that job, if you want to be a developer and you want to get that job, you got to know this class perfect. Okay, so that's very important. Okay, this class is a little bit of a combination of data structures and a lot of new algorithms we're going to see. So and also we analyze things and we have a little discrete math. So you took those courses already. Okay, I love teaching this class for the following reason. They have the cleverest algorithms. Okay, the cleverest ideas are here. here's another thing, just to fit in with wokeism and equity and all that stuff. If you have a great algorithm, and it's better than any other algorithm, it will get into this book. This is a 3rd edition book. It will get into this book. In other words, nobody cares who you are, male, female, binary, non-binary, etc., etc. Nobody cares or whatever. It's the algorithms that are important. If you'll look in this book, you'll see nothing about who invented what. They don't care. Nobody cares. They just want to make better and better algorithms. And by the way, this is something I'm going to say over and over in this class. Every time we present an algorithm, I'm going to say, can we do better? Can we do better? Okay? In other words, and a lot of times we do. Another reason why I love teaching this class, and another reason why students love this class, is because I'm going to ask questions that I can ask a 6th grader. How do you do this? How do you find the oldest person in the room? How do you find the youngest person in the room? How do you sort things? How do you search for things? Okay? We're going to do that. Okay? We know how to do it. We know some ways of doing it. We're going to see cleverer and cleverer ways of doing it. And these are problems that you can explain to anybody, and the solution exists. But these are extremely clever ways of doing it. Okay. What should you gain out of this class? As follows. You gain out of this class that if you become a developer, before you sit down and write the programs, you're going to think about the programs first. Because what you're going to learn in this class is that if you think about things and you try to do them, you'll see it comes out much more efficiently. So that's what we're aiming for. We're aiming for efficiency. Okay? And so, yes, you will do things. You'll have to do whatever, but okay. There are no slides in this class. I develop things on the board. Okay? As we go along, I develop them. But I do have to tell you a few helpful hints at studying for this course. 1, study in groups. Okay? Study in groups. Learn it no matter what. You guys, all my classes, they have student groups, they get together, they do the homeworks together, they understand things together, etc., etc. If you're on the top of the class, you might say, why do I need it? I don't need it. Well, I just got to tell you, when you explain something, you get it 10 times better. You explain it to your younger brother, your younger sister, whatever, you get it 10 times better. You explain it to other people, you'll get it better. If you're not on top of the class, you definitely want to join a group. That's one thing. Second thing is, every topic I'm going to be teaching is taught in every single college where there's a computer department. Every college has a computer department. In every college, there's an algorithms class. A lot of professors make web pages where they explain things and do different types of graphics, etc., etc. So you can find a lot of material. You type in an algorithm you don't understand, you get it. Okay? So there's a lot of stuff. Also, there are a lot of online courses with this. I told you, in every single college there's a computer department. In every single computer department there's an algorithms class. A lot of stuff. MIT OpenCourseWare has all these courses. The book that we're going to use is taught by these, the professors are MIT professors, and so that's fine. So cheat by looking online. Watch the videos, etc., etc. Okay, now let's just talk about this book for a second. This is the book, okay? And if you don't trust me, go to Amazon.com, type in textbook algorithms or algorithms textbook, okay? And you'll see this is the #1 seller. And something like, the #2 seller has something like 60 reviews, and this has something like 1,700 reviews. So this is the book that everyone uses. So students in the beginning don't like the fact that I use this book because this is not a nice, sweet book. There's no pictures in the book. There's no holding your hands and saying, hey, you know, let's do this, etc., etc. This is an adult book, okay? But it is the book, okay? And you're going to see when you become a developer on other developers, on developers' shelves or open in front of them is going to be this book. Okay, because this is the book with all the ideas, etc., etc. So you have to look at this book. You got to do this. Now, there is a certain rhythm to this book. It presents a problem. It gives you the algorithm. the next paragraph, it analyzes the algorithm line by line very nicely, and it does it. It's going to take you time to learn that rhythm of this book. It's going to take you time to learn it, but once you learn it, you'll be able to learn anything. Okay, and I'm just telling you, I've been teaching this class since 1994. And I still get students sending me emails, how do you do this and this? How do you do this and this? And I answer back, CLRS 27.2. That means Corman, Lysosin, and Rivest, Chapter 27, Section 2. And that's it. They know exactly where to look. Everyone knows exactly what CLRS. Everybody has it, etc., etc. So again, this is the book for programmers and developers. You have to get used to this book. Okay. So that takes care. That's the introduction to the class. Now we're going to get into Chapter 1 and 2. Thank you. Okay, so in the best case there are 7. Question: let's say I give you an array with 15 cards, and the cards are all in order. How many operations would you have to do? How many comparisons would you have to do? Okay, and the answer is you'd have to do 14 comparisons, right? Because the first one you assume is in order, and then you have to do 14 comparisons. Great. Now let's do something much more interesting. Okay, so in general, if you have n cards, you have to do n minus 1 comparisons. Okay, what happens here? Okay, look what happens. I assume this is in the right place, and then I do one comparison, and I say, no, you got to move this over, this goes here. That's one comparison. Now, I want to put this in its right place. Where does it go? All the way over here. So I do one comparison, and I say, no, it's got to move here. Then I do another comparison, 2 comparisons, and I put that here. That's very good. So far I did one comparison to put the second card in order. Then I do 2 more comparisons to put the third card in order. Then I have to do this. Compare, this moves here, this moves here, this moves here. I do 3 comparisons, and I get that in the right place. Okay, so you will see this is the worst case scenario. This, I have to move this here, this here, this here, this here, and do that. I have to do 4 comparisons to get that 28 in its right place. Okay, so here I have to do 1 comparison plus 2 comparison plus 3 comparison plus 4 comparison plus 5 comparison plus 6 comparison plus 7 comparison. How many comparisons is that?
Let's see.
16?
Definitely more.
No, more than 16. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28. Okay? So I have to put 8 cards in, I have to do 28 cards. This is called the worst case scenario. Why? Because the cards, the worst case, the cards are totally in reverse order, and I have to put them in correct order. And I have to do the most amount of work possible. Okay, question. Let's say I had n cards. How many cards would I have? How many operations would I have to do in the worst case? Okay, and the answer is as follows. In the worst case scenario, do you want to take this out? Okay, in the worst case scenario, this is what would have to be done. Okay, I would do 1 operation plus 2 operations plus 3 operations plus 4 operations plus 5 operations plus 6 operations plus 7 plus plus n minus 3 operations plus n minus 2 operations plus n minus 1 operation, etc. That's it. I have to do a lot of these operations. Okay, now how much is this when I have to add it up? Okay,
A lot.
a lot. Well, I don't know what n is, but a lot. Okay, so I have to tell you a story about a little boy who was misbehaving in school. And the little boy was this age. Come here, I want to show everybody how old you are. Yeah, me too. This age, he wasn't behaving in school. Okay. And this age, come here, fast. She wasn't behaving in school. Okay?
They're 8 and
Okay, he's 8 and she's 6. You ready? They weren't behaving in class, so the teacher was angry at him, and this goes back to 1870s or something. His name was 1877 or something, 1873. Okay, 1883. His name was Carl Friedrich Emanuel Gauss. Okay, he was a little boy and he wasn't behaving very well. 1777 or something. That's when he was born. Okay, so the teacher gave him to add up all the numbers from 1 to 10. Said, take a piece of paper, add up all the numbers from 1 to 10. Instead of the boy doing that, listen to what he did. He just jumped up and gave the answer. He said 55. The teacher thought he was lying, made it up, and so she kicked him out and sent him to the principal's office because he wasn't behaving. That night she went home and she added up all the numbers from 1 to 10. Let's do that. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay, 1 plus 2 is 3 plus 3 is 6 plus 4 is 10 plus 5 is 15 plus 6 is 21, 28, 36, 45, 55. 50. She saw that what the boy said was 100% correct. Okay, the next day he wasn't behaving again, and she wanted to keep him busy so that he would stop misbehaving. So she told him, take out a piece of paper and add up all the numbers from 1 to 100. Okay, that'll keep him busy. How long would it take you to add up all the numbers from 1 to 100? Answer, he just popped up and he said 5,050. 5,050. He just popped up and gave the answers. She thought he was making a joke. You know, what's all the numbers from 1 to 100? He popped up and gave the answers. He couldn't have added them up so quickly. How did he, like this, do that? Anyway, so she kicked him out. That night she went home and she added up all the numbers from 1 to 100. Guess what? What's all the numbers from 1 to 100? 5,050. Okay? She was furious. How did he get it? Okay? Anyways, the next day he was misbehaving. She figured, you know what, maybe he memorized beforehand how to add up all the numbers from 1 to 10. 10 is a typical number, 100 is a typical number. Let's give him a hard number that he never thought of. Okay? So she said, you, Carl Friedrich Emanuel Gauss, you're not behaving well. Add up all the numbers from 1 to 376. Okay? And like this, he jumped up and he gave the answer. She didn't believe that he gave the right answer, so what'd she do? She sent him to the principal's office. But that night was the weekend, and she had a whole weekend to add up all the numbers from 1 to 376, and you know what? He was 100% right. Okay, so I'd like to teach you the trick that he did, that he was able to do it very, very quickly. Capish? Okay, so here's the trick. You see, Gauss was a 5-year-old boy, but he understood what we learnt, namely, A plus B is equal to B plus A. A plus B is equal to B plus A. Okay, what does that mean? Doesn't matter how you add numbers. The first and the second is equal to the second and the first. 5 plus 3 is the same thing as 3 plus 5. Nothing shocking there. But what Gauss understood at the age of 5 is, it doesn't matter how you add up numbers. That's what he said. So let's do this. Okay. Let's say you wanted to add up all the numbers from 1 to 100. Rather than doing it like I would do it and you would do it, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, look what he said. He said a plus b is equal to b plus a. I can add these in any order I want. Watch. 1 plus 100 is how much? What's 1 plus 100?
101.
101. What's 2 plus 99?
101. 102.
No, 101. What's 3 plus 98?
101.
101. What's 4 plus 97?
100.
101. They're always like that. So he said like this, instead of adding, and they keep on going, question, instead of adding them in order, add them out of order. Okay? Now, how many pairs do you have for this?
50.
50, because you took 100 and you split them in two. So you have 50, and each pair gives you 101. So 50 times 101. All Gauss had to do was figure out what 50 times 101 is. That's 5,050. That's the way he did it. And if I gave you from 1 to 376, how would you do it? You'd say 1 plus 376 is 377. Okay? And then you have to figure out how many divisions divided and do that. Okay, same thing here. Let's erase this. In the general case, same thing here. You ready? 1 plus n minus 1 is n. 2 plus n minus 2 is n. 3 plus n minus 3 is n. Dot, dot, dot. Okay? So if you want to add up, this is the way we're writing up add up. I is equal to 1 to n minus 1. Well, of I is equal to n. And how many pairs do you have? N over 2 pairs. No, n minus 1 over 2 pairs. Okay? And I just want to write that out a little bit more. That's n squared minus n over 2. You'll see what I mean by this at the end of next chapter. That's about n squared. Okay? That's his trick. That was his trick to add up numbers very quickly. You do for the first and the last, and the second to the first and the second to the last, and the same thing, and you get that out. Okay, so that's a very nice trick. Okay? I just want to do it another way. I want to show it to you another way. Okay? Let's say we do 1 to 10. So look what I do. I do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9
plus 10.
plus 10. Okay, and now I ask how many dots are in this box? Okay? Okay, and the answer is as follows. How many dots do you have across? 10. How many dots do you have down?
10.
How many?
9.
What's no? Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. How many is 10 times 10?
100.
100. Okay, so we don't have 10 times 10. We have not 10 squared, but about 10 squared over 2. Half of that. But it's not really that. Okay? The point is, how many squares do we have? How many dots do we have? About n squared over 2. Okay? Not exact because we have the whole diagonal. So it would be, if I chopped up half of these, half of them would be on, half of them would be off, then I would. Okay? So it's n squared minus n, that's this thing, minus n over 2. So that's what we have. Okay, anyways, that's a visual way of seeing what this thing is. But let me just tell you, from an algorithm's point of view, what little Gauss did. Okay, let me just tell you from a little algorithm's point of view what he did. He said, look, how does the teacher do this? She does 1 plus 2 plus 3 plus 4 plus 5 plus 6. She's going to do about 100 additions. Okay? Now that takes a long time to do 100 additions. Gauss's trick says, no, you don't have to do 100 additions. Here's what you have to do. You have to do n times n minus 1 divided by 2. So here's what you have to do. You have to do one subtraction, and that's a pretty easy one. You just subtract 1. Okay? You have to do one division, and that's a pretty easy one because all you have to do is divide it by 2. And the big thing is you have to do one multiplication. One multiplication instead of 100 additions. What's quicker to do? Gauss's trick or your trick? Gauss's trick. So we do Gauss's trick. Make sense? Okay. It's going? The video is going? Okay, great. Now let's go back. What were we talking about? Why were we doing this? We said when you have a problem, you can analyze it two different ways. You can ask, what's the best case scenario? And you can ask what the worst case scenario is. There's another way also. Okay? And just for the insertion sort, we saw the best case is about n. The worst case is about n squared. I'm going to write about. We'll explain what I mean by about in a minute. Not in a minute, in an hour. Okay? But there's another question we could ask also. Average case. In other words, what happens on average? What happens when I have a bunch of cards? Some of them are in order, some of them are not in order. How much work has to be done? And the answer in this case is about n squared. It's still about n squared. So there's a lot of work to do. Now we're going to see that we're going to do, in this class, we're going to always talk about what's the worst case scenario. The best case scenario, that's not interesting. Okay? That's like when you go buy a car and you ask the guy, when you're about to buy the car from the used car salesman, what's the best case scenario? And I'll tell you, the best case scenario is the car is going to live for 3,000 years. Okay? That's not interesting. What's interesting is what's the worst case scenario? In other words, when is the car going to drop dead? Okay? When's the car going to stop working? Okay, so we're always going to ask what the worst case scenario is, and sometimes we're going to talk about what the average case scenario is. But the book goes through it very carefully, all the different scenarios.
That's the worst, the average.
Okay, want to do a few more things before we go on. Okay, so this is something we're always asking. Okay, whenever we meet an algorithm, we want to know how much work is done. And the answer is, it depends on two things. One, how big is your input? And two, how ordered is your input? How good is your input? Etc., etc. So how big is your input? That's, if you have a lot of cards, it's going to take a lot of time to put them in order. If you have a few cards, it's going to take less time to put them in order. Okay? And also, we're not only just interested in the number of cards, but how bad is it? How disorganized, how organized it is, etc., etc. We're usually interested in the worst case scenario. What's the worst way that the cards can be organized? Okay, this is what algorithms are all about, and I'd like to talk to you, just list off certain things. Sometimes I write it, but you have a video, so I'm going to say it more than write it. And the book does this very, very neatly, and the book goes through these different problems and discusses these things very carefully, and you have to read the book anyway, so you're reading the book. Okay, so here's certain things that we care about. Searching for a number in a list. Let's say I give you a long list, and I'm searching for a thing in the list. Okay, the size of the array is how big the problem is. If I give you a giant array with 10,000 elements, that will take time. If I give you an array with 3 elements, you look for this one, you look at that one, you look at that one, you look for 3 things. It's very easy. Okay? We're going to talk about multiplying 2 matrices. Okay? and you have to know what matrices are. If you have two matrices, well, how big is the input? Depends on the size of the matrices. How big are the matrices? You can have 500 by 500 matrices. You can have 3 by 3 matrices. Okay? And the operation there is multiplying numbers. Sort a list, we just did sorting a list. The input size is the size of the list. How many comparisons are done? That's what the operation that we're considering. Going through a binary tree. You know what a binary tree is? You took data structures. Well, how many nodes in the tree? Or how many leaves in the tree? There's also comparisons. String matching. Every time you press Control F on your computer, you're doing a string matching algorithm. We're going to do that in chapter, I think, 28 or something. We're going to go through several different string matching array algorithms. I'm going to see how it's done and how it's done efficiently and why we should do this string matching array algorithm and not that one. Okay? But there it depends how big is the text. When you have a book and you're searching through it, it's going to take a long time. Anyways, Google makes their money by doing this very well. They search through millions of web pages and finds the string that you're looking for. Okay? Evaluating a polynomial, that's something else. Okay, I'd like to do another algorithm now that's not done in this book or in chapter 1 and 2. It's done later on. And I want to talk a little bit about that and see why we're doing it. Okay, so I'm going to assume you know what matrices are, and I'm going to assume you know what matrix multiplication is, how you multiply matrices. Okay, and now I ask you the following question. What's an algorithm to multiply matrices? So let me just remind you a little bit about matrices. Here's a matrix. Okay, it's an array of arrays. It's a thing like that. It's like that. Here's another matrix, and let's assume this is n by n, and this is n by n, and so we get out C, an n by n matrix. Okay, so we know how to multiply numbers, but how do you multiply matrices? And the answer is very simple. You want to figure out the ijth position over here. Well, you take the ith row here, you take the jth column here, and you take this and you multiply it across. This times this, plus 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 this times this, etc., etc. Okay, let's write an algorithm that does it. Okay? Okay, you have to add up all those numbers. But I'm doing this for a reason, even though the book doesn't do it, but that's fine, because there's a lot of things to do. So here you do it. For I equal 1 to n. For j equal 1 to n. Cij equals 0. That's going to be our counter. So basically, we're going to have to fill in, here's your A, here's your B, equals C. We're going to have to fill in every single thing in here. So we have to fill in every row, that's every row, every column, and here, we first start off when you add up a bunch of things, you have to start off assuming that your equals 0. Your sum is equal to 0. Okay? And then you do the following. For k equals 1 to n. Okay, and then you do the following. Cij, those are subscripts. No programming language in the world uses subscripts. But we're not interested. We're not using programming languages. We're using pseudocode. Is equal to Cij plus Aik times Bkj. Okay? Okay, that's a little bit complicated. That's a little scary looking, but that's what it does. Okay? Basically, again, this this column and this row are used to determine that box. Okay? And the k does that little dot dot. This times this, plus this times this, plus this times this. That's that. Okay? This is a 1, 2, 3, 4, 5 line program. Question, how much work is done? Okay? And the answer is as follows. Look, this, what do you mean by work? I mean how many multiplications are done. That's your main operation. Okay, that multiplication. Okay? And the answer is as follows. This loop does n times. But how many times do you do this loop? You do this loop n times. So this algorithm, without that line, is n times. And each one of them you do n times. And how many times do you do this whole thing? Answer n. So the algorithm is n to the third. Okay? It takes n to the third operations to do that. N times n times n.
We didn't have that.
Say, say again?
We didn't have that.
No, we didn't learn exponentiation, but they know it. Okay? N to the third. Okay, now you ask yourself, that's the worst case scenario. What's the best case scenario? And the answer is the best case is equal to the worst case is equal to the average case is equal to n to the third. No matter what, it's n to the third. Okay? It doesn't matter if the numbers are big or small or et cetera, et cetera. It doesn't matter how the numbers are organized. The reason is because there's no if statements here. There's no comparisons here. When we were doing the insertion sort, so we said sometimes we do this, sometimes we do that. Here we're always doing n to the third operations. And because of that, it's done. Okay, now I'm going to say something that I'm going to say every single day the rest of the semester. Can we do better? Can you write an algorithm that's better than n to the third? Okay?
And to the fourth.
And to the fourth, that would be worse. That would have to do more work. Okay? So there's an algorithm that does n to the 2.7. We're going to actually see that algorithm. It's called Strassen's algorithm. We're going to do it in chapter 4. It multiplies two matrices in a quicker way. Okay? The world's record is something like n to the 2.3 or something like that. And it makes a difference. Now let me just tell you a cute little trick that you can do. Psst, go get me my cell phone. It's right over there. A cute little trick, my cell phone. A cute little trick that you can do right away. This is a 5-line program. Okay? This is a 5-line program. Okay? Now, when you get a new computer and you want to, you know, when you get a new car, you want to take it out on the highway and get the gunk out of it. You want to just run it really quick a lot. Okay? Same thing here. You want to do this really, you get a new computer, you want to get the gunk out of it. You want to see how much it is. So here's something you can do. Take a random 500 by 500 matrix. Okay? Not a 3 by 3, not a 4 by 4, a 500 by 500 matrix. Put in it numbers. Make sure that some of those numbers are negatives, because otherwise you can just have positive numbers and you're going to get bigger and bigger. You don't want to do that. Some negatives, some positives. You really want to do this, you should do it with real numbers. All real numbers between 0 and 1. Between -1 and +1. Okay? A 500 by 500 matrix. Take that matrix and multiply it by itself 500 times. That means do another loop that does inside that loop, you do this. Multiply it by itself 500 times. So that's going to be another thing. What's before I? A, B, C, D, E, F, G. For G equals 1 to 500. Okay? Multiply the matrix by itself 500 times. Now, this we saw was an n to the third algorithm. Okay? With this extra line, it's going to be an n to the fourth algorithm. Okay? Now, let's do that. So if n is equal to 500, okay, what's 500 to the fourth power? Baruch, what's 500 times 500 times 500 times 500? I don't know either. That's why I need the computer.
No.
Okay, 500. Oops. I'm gonna put it,
Times 4.
times, no, not times 4, to the fourth power. That means 500 times 500 times 500. It's equal to 62.5 billion. Billion. See? 62.5 billion. Okay? So you're going to do 62. Here's a quick way of writing a 5-6 line program that you can get 62.5 billion operations, okay? And how long it'll take. So that's an interesting. A long time, right?
Dave,
We're going to see in a few minutes. Okay, so this is matrix multiplication. It's a lot of fun. I'd like to show you another algorithm that does. You know what? Let me just take a minute break. Okay, so one more algorithm, and then we'll do some problems. Okay, this is another algorithm to sort things. It's called merge sort. It's on page 38 of the book. I'm doing it because it's a recursive algorithm, and I just want you to get a feel for that. We're going to spend a lot of time with recursive algorithms in chapter 4, but I want you to get the first thing. And the idea is as follows. Okay, you might have seen it before. You should have seen it before. If you have an array of numbers and you want to sort them, okay, so the array is A, and it starts at P, and it ends at R. So here's what you do. If P is less than R, in other words, if you're less than that, if the starting point is less than the ending point, then what you do is you find the midpoint. What's the midpoint? P plus R divided by 2, the floor of that. That's the midpoint. So we're going to call that Q. And you see here, P is the beginning, Q is the middle, R is the end. Then what do? Now you have two arrays. Okay? The first part and the second part. Okay, so here's what you do. You sort the first part, then you sort the second part. That's this line. From P to Q, and then from Q plus 1 to R, that's the second part. And then you merge them together, and you keep on doing it. Now, the question is, how do you sort the first part? Well, you split it in half. Well, how do you sort? Then you sort this, and then you sort this. Well, how do you do that? You split it in half, 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 you split it in half. We're going to do an example in 1 second, but this is the main idea. Okay? So let's do some things with cards. We love cards. Okay? So we have 8 cards, not in order. Okay, Miriam, did we get everything in the cards? All the cards in? 15, 18. Okay, so here's what we do. We split the cards in half. We have the left side and the right side. Okay. Okay, now we have to sort the left side. How do you sort the left side? Well, you split it in half, and you have the left side and the right side. Great. How do you sort this? Well, you split it in half. Okay, and now you have this and this. Okay, now this by itself doesn't have any more P less than R. It's not less than R. Oh, sorry, 1 second. Okay, so now we have to merge these together. It's very easy to merge two things. It just takes, if you have two things each size together that have n, you merge them to bring them together. Same thing here. You have to sort. This is sorted, merge it together, you get that. Okay? This is sorted, you merge it together, you get that. This is sorted. To merge them together, you got to do this. Great. Now, this is a sorted list, this is a sorted list. Let's bring it together, and it's very easy to sort. That's this algorithm. It's on page 31 of the book. Okay? And so we get that. This is sorted, let's merge them together. It's very easy to merge things together, we get that. And now we can merge these things together. Okay. I'm not doing it because we'll talk more about merge sort later on. The reason why I'm doing it now is because I want you to get that feel of recursion. A program that calls itself. Okay. Now, question. How much work is done? How many operations do we have to do? How many swaps do we have to do? Okay, and I want to show, I'm doing this because I want to show you this analysis. Okay, well, again, how many swaps do you have to do? Well, it depends how many how many cards you have. So let's say I have n cards. How many swaps do I have to do? Okay, well, if you see what it did, how did this algorithm work? It did the left half plus the right half plus, to merge them together, we'll just write n for that. Okay? Now, that doesn't really tell you how much work is done, because look what I did. This is a function. This is not really a function, because I plug in t of n. I don't know what to do here. Okay? Usually a function says f of n equals something, and you can figure it out. But notice, this is like a recursive function. The function calls itself, which is exactly what it does. It's called the recurrence relation. We'll see that later on. You can add these two together, plus n. Okay, now again, this is not a function. We will see later on in chapter 4 how to make this a function. It turns out that this becomes n log n. We'll talk about log in chapter 3. We'll deal with that. So, how much work is done? N log n. That's a lot better than n squared. We'll understand that later on. Okay, so this is a nice algorithm, and it uses recursion. Great. Okay, let's just finish up with one more idea. We don't need the cards anymore, but we will have one more idea. And this is, in chapter 1, they talk about this, and you have to do homework problems like this. And the idea is as follows. I ask you how fast the algorithm works and things like that. Okay, so let's go through this. Okay, I'm going to go a little bit quickly here because I have the answers, and also because you probably have seen this in a data structures course, and that's good. That's why we do it in the beginning. It's also part of something I gave you out in the handout called Homework 0. You have to work out the problems and give me the answers. Okay, so let's say you have a computer that does 68n to the third operations. Go get Mark. You would want to see this. You have a computer that does 68 n to the third operations in a you have an algorithm that demands 68 n to the third operations. That's how many operations it demands. Okay? And you have a computer that does one operation in a microsecond. Okay, that's equal to 1/millionth of a second. Okay, so you can do 1,000,000 operations in a second. That means each operation takes 1/millionth of a second. Okay, and now we ask the following question. How long will it take to do an input of size n equals 1700? Okay, and this is pure math. There's nothing intelligent here whatsoever. It's bookkeeping, and again, it's something I expect you to be able to do, and so I just want to do it once to get a feel for it, and I promise you will be on the first test. Okay, so let's do it. F of n is equal to 68n to the third, so f of 1700 is equal to 68 times 1700 to the third, which is equal to, again, calculators, 3.3408 times 10 to the 14 operations. Okay, but it can do 1,000,000 operations in a second, so that becomes 33408 0.4000 seconds. Divide 10 to the 14th by a million. A million is 6, is 384 million seconds. Okay, divide by 60, because you're not interested in how many seconds, but you're interested in how many minutes. You get 5.568066 minutes. You're not interested in minutes, you want to know how many hours, so you get 92801 hours, 92,800 hours. This becomes 300 divided by 24, you get 3,866 days, which is equal to 10.59 years. Okay? That's how long it'll take you to do this thing. So again, you give it a computer, that's a pretty standard speed of a computer. It's actually now slow, whatever. You're given a size, an input of size 1700. It's going to take 10.59 years to do. Now, I just want to go to the side of the board for a second and say, you know what? Let's say that you actually thought about this problem and you didn't just do the regular algorithm, but you took Yanofsky's algorithms class and you thought about it and you did a clever part of the algorithm, you did something really clever with the algorithm, and you got another algorithm that does it in g of n, which equals 68n squared operations. So instead of n to the third operations, you need n squared operations. That would be much better. Okay? So let's just see how long that would take. So let's do it. G of 1700, same size, on the same computer, is equal to 1.9652 times 10 to the 10 operations, which is equal to 19652 seconds, divided by a million, because you can do a million operations in a second in this thing. Okay, which is equal to 327.53 minutes, which is equal to 5 hours and 45 minutes. Okay? Okay. So, if you actually think about it, you're going to do the same operations, but instead of doing it in 10 years and 10.59 years, you're going to do it in 5 hours and 45 minutes. Okay, now your boss goes over to you and he says to you, I want you to do this and this. You come over to him and say, you know, I didn't really think about it, I programmed it, and it'll take 10.59 years. I'm going for lunch. Okay, you do that, your boss will say, don't come home from lunch, okay, because you're fired, finished. Okay, but if you spend time thinking about it and you get the algorithm to 68, instead of 68n to the third, 68n squared, that's much better. You could say, okay, I'm going to lunch, I'll be back in a little bit, and it'll be done. You got your job. Okay, so you like that. Okay, now I just want to give you a trick of what's going on here, just an insight on what's going on here. There are 4 things going on here. There's speed of algorithms. 2, there's speed, I shouldn't say speed of algorithms, say efficiency of algorithms, how efficient it is. Speed of computer. 3, speed of computer, who's that? Okay, and then there's size of input, and 4, there's time. Okay, so with all of these, I can give you 3 of these pieces of information, and you have to figure out the 4th piece of information. Okay, here I tell you what the efficiency of the algorithm is. I tell you what the speed of the computer is. I tell you the size of the input, and we calculated how much time it is. Okay, we then change the efficiency of the algorithm to something else, and we saw what that is. But this is what's going to be done. This is what's done and going to be done. I always tell my students, this explains every physics problem, every science problem in undergraduate and high school. Okay, they give you n-1 pieces of information. You know some equation. You have some equation to do it. You plug in the n-1 pieces. They ask you for the nth thing. You get it out. Okay, that's all physics, chemistry. It's pretty easy. Okay, same thing here. Let's just do one more type of thing. But here, I'm going to give you other information. Okay. I need my eraser. There it is. Okay. Okay. Let's do another problem, very similar. The algorithm is 68 n to the third operations. That's how many operations are needed. Okay? Same computer as before. Okay? That means it does one operation in a millionth of a second. Okay? And now I can ask the following. How large of an input can be done with this algorithm on this computer in 5 hours? So here, I give you the efficiency of the computer, the efficiency of the algorithm, I give you the speed of the computer, I give you the time, and I'm asking you for the input size. Okay? And the answer, how large of an input can be done in 5 hours? And the answer is as follows. 5 hours equals how many minutes? I can't do this. 300 minutes, which equals 18,000 seconds, which equals, if you have a computer that does 1,000,000 operations in a second, so you have to calculate how many operations. And so you get, this is 1.8 times 10 to the 10 operations. Okay, great. And now you have the following. You know it works like this. So this is how many operations you can do in 5 hours. And you want to know 68 n to the third equals 1.8 times 10 to the 10 operations. Okay? Okay? Now all you do is solve for n. So you get n to the third equals, again, calculate. You need a calculator for the test. N to the third equals 2, 6, 4, 7, 0, 5, 8, 8, 2. Okay? Take the cube root of both sides. You get n equals 642.07. Okay? By the way, let's do the same problem, but instead of for f, let's do it for g. G of n equals 68n, n squared operations. Okay, well, you're going to get number of hours. You want to know the same question. Okay, the same thing here. You're going to get 5 hours is 300 minutes, whether you do it on this algorithm or this algorithm, which is equal to 18,000 seconds, which on this algorithm or this algorithm. Okay, and so you get as follows: 68 n squared equals 1.8 times 10 to the 10 operations. Solve for n, you get 16,269. Okay? You would rather do it on this algorithm than this algorithm, because here in 5 hours you'll only be able to do 642. In this algorithm you'll be able to do 16,269. Your boss is going to like you a lot more. Okay? Okay, so that takes care of that. Now, at the end of Chapter 1, you have to do a lot of these things, and also in the handout I gave you, Chapter 0, I'm sorry, it's called Homework 0. There are 3 problems just like that, and I promise you on the first test there will be a problem like this. I will give you 3 of the following 4 things: the efficiency of the algorithm, the speed of the computer, the size of the input, and the time. 3 of those 4 things, you're going to have to figure out the 4th one. Okay? Anyways, welcome to Analysis of Algorithm. It's going to be great fun. We're going to do a lot. Take care.